So again, if you did struggle on that test, please make sure you get with me or get with the tutoring lab, get with something, right? I can't force you to come see me. I can't force you to come get help, but I'm telling you, if you did not do well, let's try and patch the holes if we can, okay? All right, so what are we doing? What are we doing today? Integration by parts. So we had started integration by parts, right? We had started it, and we didn't quite get through a lot of the more challenging problems. I did go back and look at the video to get an idea of where we did stop. Yeah, exams are up here if you want to come pick them up. So let me put a problem up on the board here for you. And where is it? There we go. We had finished, I'm just going to put it off camera here. We had done this problem, right? We had also done, I think, natural log x dx. We had done those two. Which one did I finish with? Natural log? Yes. Okay, so I'd done that one, I think, before, and then I did this one, right? So what I usually do before I come to class is I go, just look at my video, and I'll just skim through it, just skip through the video and just kind of see what I did, just to make sure. Not a bad idea for you as well to just kind of review what we did the last class, especially after a test, because it's been a while. But I'm going to pick up just like where we left off. So we're doing integration by parts. I have another problem for us to do here. And this one is a classic problem, all right? This is one of those problems where every student needs to see this. I want to do it exactly like it is in the notes. Every student needs to see this because, like a lot of things in this class, until you see it happen, you really don't know how crazy some of this can become, all right? So I'll show you an example here. There we go. And the formula, remember, is that if we have an integral where we have u times dv, this will be equal to ultraviolet minus the integral of v du, ultraviolet minus voodoo. So what we're trying to do is we're trying to look at the integrand, we're trying to identify some function u, that in the new integral we're going to be dealing with its derivative, and then in this original integral we're looking at the other function is the derivative of some function that's going to be in our new integral, right? So one of the functions we pick in the new integral, we see its derivative. The other function we pick in the new integral, we see its antiderivative, right? So it's transferring, switching of the derivative. All right, so we look at this, and we first have to realize we have to use integration by parts, right? I mean, we have to eliminate basic u substitution, right? That's not going to work. Why isn't basic u sub going to work? If, let's just say you picked u to be cosine x. What's its derivative? Negative sign. Do you see the negative sign? No. What if you pick e to the 2x as your u? Then you would need the derivative, e to the 2x again, but you've already used this, so you'd have to see its derivative there as well. So we can't use basic u sub for this. So the only other thing we have is that. So let's try it. So I'm going to have to pick a u and a dv. And by looking at your test, I can tell that some of you have either learned this a different way, or maybe you got tutoring, or I don't know what, watched Khan Academy, I don't know what. But everyone does something a little different for integration by parts. This is the way I do it, all right? So I have my table. I need to pick a u and I need to pick a dv. Now I'm thinking right now that whatever I pick for u, in the new integral, I'm going to see its derivative, right? So let's say I pick that for u. That means in the new integral, I'm going to have the derivative of this, which is going to be basically itself, right? So I know that if I pick this in the new integral, the derivative of this is itself, okay? And then that forces this part to be the dv. And so in the new integral, it'll be the antiderivative of this, which would be sine. So what does that new integral look like? It's got almost the same, right? It's got e to the 2x in it, and it's got a sine x, which isn't much better than this, is it? Okay, so let's try it the other way. What if we pick the cosine x to be the u? then what's the derivative of that? Negative sign, so that'll be in the new integral. And that forces the e to the 2x dx, these two pieces, to be my dv. What's the antiderivative of e to the 2x? What's it going to have in it? E to the 2x, right? So do you see that in that new integral, no matter which way I do it, the new integral is going to have e to the 2x in it, and it's either going to have like a sine or a cosine, which, well, it's going to have sine. So it doesn't seem like it's going to get better. Do y'all see that? But I've got to try something. So I'm just going to go with one of them. I'm going to go with, let's do this one, e to the 2x here. Let's go cosine x dx. So I'm choosing again, just to be clear, I am making the choice that this is my u and that everything over here is my dv, right? Tests are right up here if you want to grab your test. All right, so now once I have chosen my u and my dv, I'm going to go ahead and differentiate to get du. And the derivative of that is 2e to the 2x dx, because the derivative of e to anything is itself times the derivative of what's up here, which is 2. And then, of course, you have to put the dx. And then the antiderivative of cosine of x with respect to x is sine x. So v is sine x. All right, so here's where we are. This integral becomes, right, I'm using the formula now, ultraviolet, so u times v, that's these two multiplied together, e to the 2x sine x, minus the integral, and I always like to leave a space in front of the integral because I might have a constant that I'm going to pull out. Now I'm going to do dv, right? I mean, sorry, not dv, v du, which is this, that's du, this is v, right? V times du, or these two multiplied together. When I multiply what's in red together, I do see that I have a 2 here, right? And that 2 can come out of the integral, so I'll put it right here, 2. And then I have the e to the 2x dx times sine, and because they're all being multiplied, I can put those in any order I want. So I'm just going to put them kind of in the order that the original integral appeared. E to the 2x first, then the sine x dx. Yes?
When you pulled out the 2, why don't you have to do it
Because I'm not trying to scale it. It's not like when we did basic u sub and we're like, okay, we're missing a 2, I need to divide both sides. We're just taking these two and multiplying them, so the 2 would be here, right? And when you have a constant inside of an integral, the constant can just come out. So it's just like with the derivative, the constant came for the ride. With the antiderivative, the 2 is just going to come for the ride, so we may as well just bring it out. All right? Okay, any questions on this? Have we actually like gotten anywhere here? Not really, right? Because this new integral is no better than the original one, is it? Right? It's no better. So what do we do, right? I mean, we did see with this problem over here last class, we did see that it might be the case that we have to repeat integration by parts more than once, right? But over here when we did this one, the reason we did integration by parts twice is because the first time we did it, it brought the power of that t down by 1. And then we did it a second time, the t went away. So that's why we did integration by parts twice there. It kind of chipped away at the power of the t. Here, there's no chipping away of any powers. Do y'all see that? Because we know that this is not going to go away. But we're still going to do it again. All right? We're going to do it again. So I'm going to let's do it in blue here so we can really focus our attention. I am going to just do this part right here, right there, as its own problem right here. Okay? Integral e to the 2x sine x dx, right? And I'm going to start over. I'm going to do integration by parts again, not thinking that this is going to get me anywhere. And now I have to choose my u and my dv. So what do I choose? Well, you might think, all right, let's do the opposite of what we just did, right? Like since we chose e to the 2x here, maybe if we choose the opposite this time, it will get us somewhere. Well, it turns out if you do the opposite, in other words, if you let the u be the sine x and then the dv be the e to the 2x dx, if you do that, you go right back to the original problem. Like everything cancels out and you get this right back. So I'm going to do e to the 2x. Now the only way you know that is because I'm telling you that, right? Like you would have to try that yourself to see that it wouldn't work if you put the sine x here. There we go. That's what I'm going to do. Now let's just crank this out and see what happens. du is 2e to the 2x dx. We've already done that before. And the antiderivative of sine, careful here, antiderivative of sine would be negative cosine, right? All right. And now we can say that this integral becomes, we're going to do ultraviolet, these two multiplied, right? Ultraviolet, these two multiplied. So when I multiply those two together, I think I'll write it this way, negative e to the 2x cosine x. I just moved the negative in front of the cosine out in front of the e to the 2x. Then I have minus, okay, integral. So I'm doing ultraviolet minus the integral of voodoo. Voodoo is going to be this and this together, right? Can I pull anything out? I can pull a negative 2 out, can't I? I have a negative here and I have a 2 here. I can pull that out, and what will this become in front here then? Plus 2. Plus 2. Because I'm pulling that negative and that 2 out. And now what's inside the integral still? E to the 2x cosine x dx, right? And then you go, shit. That's the original problem, right? That's the original. So now in order to solve that integral, we have to solve the same integral. So doesn't it seem like we've gotten really nowhere? Okay, it seems that way, but we actually were there. Okay, so let me show you what we're going to do now. Let's go back to this line right here. And what I'm going to do is I'm going to take what's in this bracket. That's everything over there, right? I'm going to plug it in right here. Let's just see what we have. Let me do it. Yeah, let me just continue it here. I need a little more space. So equals, I'm just rewriting this, e to the 2x sine x minus 2. Okay, I'm going to go ahead and put it in brackets. Now I have minus e to the 2x cosine x, okay, plus 2 integrals, right, of e to the 2x cosine x dx, and then close the bracket. Y'all agree with that? That's just me plugging this blue piece in to what I just did over there. All of this just got replaced with that, so I still have the minus 2 in front of it all. There it is. Yes?
The first problem, wasn't it supposed to be, I mean, not the first problem, when we just did it, it's supposed to be u to v, so would that be e to the 2x and then sine?
Wait, where? Are you talking about here or up front?
Oh.
This is u times v.
Oh, yeah.
U times v.
Thank you.
Yep, no, it's okay. So ultraviolet, these two, minus the integral of voodoo. All right, good? Okay, next thing I'm going to do is I'm going to clean this up a little bit. I'm going to go ahead and take this all out of here. Okay. I'm going to do it above this line. Equals, okay, I'm going to go ahead and distribute the negative 2 through. So it's going to go here, and it's going to hit that 2 in front. And that's it. So let's do that. So we'll have, oops. We'll have e to the 2x. Well, you know what? I'll put it all the way up here. No. I'm not going to do that. Sorry. E to the 2x sine x. Okay, distributing through here. Minus and minus is plus. So plus 2e to the 2x cosine x. And then negative 2 times positive 2. So minus 4 integrals of e to the 2x cosine x dx. Yeah? Again, we sit here and we go, well, what are we going to do? Why not do it again, right? Why not do integration by parts again? Here's the key. Here's the key to getting this problem. You have to realize right now that we're saying that this is equal to this, right? Saying that this is equal to this. So what I'm going to do, and I don't know how you can do this on your paper, I'm going to rewrite this. I'm going to rewrite the original problem right here. Okay, there's my original problem, and I'm going to put it equal to this right here. This is where we are. I want it side by side like this so I can show you what we're going to do next. If you write it like this, right? If you write it like this, this is an equation, isn't it? And can't you do, like, when you have an equation, can't you, like, add or subtract something from both sides? As long as you do it to both sides? Right? So do you see I have minus 4 of these integrals over here? Can't I add 4 of these integrals to this side to make it go away? As long as I add 4 of those integrals to this side. That's what I'm going to do. Another way to look at it is, okay, I've got one of these apples, right, is equal to blah, 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 minus 4 of those apples. So I'm going to add 4 apples to both sides. So I add 4 of these integrals. I have no idea what these frickin' integrals are, but I just know that I can do this algebraically, right? I add 4 of those integrals over here. It goes away here, right? Because you're adding the opposite. And how many integrals do I have over there now? I have 5 of them, right? I have 5 of them. So that means I have 5 of the integrals I'm looking for is equal to e to the 2x sine x plus 2 e to the 2x cosine x. Do you see that this side no longer has an integral in it, right? And so if I want to know what the answer to this is, the only thing I need to do is resolve this 5. How do I resolve this 5? Yeah, it's being multiplied, right? So let's just divide everything by 5. So divide this by 5, divide this by 5, divide this by 5. That's a 5. And so we get our final result, which is the original integral we're looking for equals, okay, when I divide this by 5, it's the same as multiplying by 1/5, right? So I'm going to write it that way instead of dividing by 5. And then over here, dividing this by 5 is the same as having plus 2/5 in front. And then e to the 2x cosine x. I'm missing something. Plus c. Now, this is a little bit tricky in this problem because did I actually ever find an antiderivative? I mean, other than the integration by parts part, did I ever actually have to, at the end, find an antiderivative? No. So I have to remember that, you know, even though I did this like clever little trick here, I'm going to have plus c. Like, I have to, because this is the answer. I have to remember to put plus c here. That's weird, right? If this is the first time you've seen that, that's weird, right? Because it required integration by parts twice to make the original integral we were looking for appear. And luckily, it was minus 4, right? Minus 4 of them, so I could add that to both sides. What if that integral would have appeared? What if this integral would have appeared over here, but that wasn't minus 4? What if it was just plus that integral? Could I have done this? If it was just plus that integral and I had this integral here, could I have subtracted this integral over here? Yeah, but then what happens here? It goes away, right? And that's what would have happened had you done, remember on the second integration by parts I said if you switched it, it wouldn't work? That's what would have happened. So The fact that this was minus 4 is like, yes, because now I can add it to both sides. So I call this problem the rabbit out of the hat problem because it's like magic, right? It's like we're just like, whoa, there it is, okay? So you've seen this now, yes? What would tip you off? If we go back to the original problem, what would kind of tip you off that we would be using this method? What do you think's like the kind of giveaway to you? The fact that whether or not you differentiate or integrate either one of those, you're going to wind up with either itself or like sine or cosine, right? Like nothing goes away. Like back here in this problem right here, right? If we choose if we choose that to be u, we take its derivative, it becomes 2t. So the power changes. Everything, we actually get some changing happening. Does that make sense? Here you don't get any changing. Both of these functions are what we would call cyclical. Meaning if we take derivatives, we just kind of keep getting the same thing, or we get a pattern of things. So nothing vanishes, nothing gets better. Interesting, yes? Guarantee you're going to have something like that on your next test. Promise 100% you will have something like that, all right? Okay, fun. All right, let's look at our next example. All right. Integral e to the square root of x dx. I think what makes this class challenging is that, and I think you're hopefully starting to see this, that it's not like Cal 1 in the sense like we don't have product rule, quotient rule, chain rule. It's not like just like follow the rules, right? You have to look at the problem, you have to analyze it, you have to get like, you have to feel like you can get it. Like you have to like have that confidence. You know what? If I throw enough effort at this, I'm gonna get it, right? And you gotta be prepared to not get it a few times and start over. I've told you this, right? So it's a very different type of thinking than Cal 1. All right. So you look at it and you look at it. Okay, let's think like basic U sub, right? We don't want to lose sight of the fact that we do have basic U sub. So what could you choose for U here? Like what would be a natural choice for U if you were going to do just basic U sub? Square root of x? But the problem is, what's the derivative of the square root of x? 1 over 2 root x, right? Do you see that anywhere? No, right? It's not there. So it's looking like basic U sub is not the way to go, right? Any other basic U sub? Could you choose the whole thing for basic U sub? Well, then you need the derivative of that, right? Which would be itself and then some other crap, which you definitely don't have here, right? So you'll see basic U sub doesn't look right. All right, what's the only other thing we have? Integration by parts, okay? If you do integration by parts, what are you going to choose for your u and your dv? Let's just try it here. If I choose this to be, what are we going to choose u and dv to be? E to the root x for your u, and that would force this to be just 1 dx. That's really the only choice you have. The only other thing you could think to do is this. You could do this. You could put the e to the root x dx here and just put what? Well, that would force what? This to be what? A 1, but there's a major problem here, right? Because what's the derivative of that? 0, and then voodoo is going to be gone, isn't it, if that's a 0? So, and then also, can you integrate that? No, that's the original problem. So that's a no-go, right? Do y'all see that? That's a no-go. So this is pretty much all you've got. All right, so let's try this. Let's just see what happens. Let's do the easy part first. If I go from here to here, what's the antiderivative of 1? X. Okay, now we have to take derivative of e to the root x, which is itself, times the derivative of what's up there, which is 1 over 2 root x dx. Yuck. Do y'all see why I'm saying yuck? I'm only saying yuck because I'm already thinking about voodoo. I'm thinking about what this times that's going to be, because that's the big thing that's in my new integral, right? That's the piece that I multiply and that becomes my new integral. And do you like that new integral? Yeah? I'm going to write it down. Let's just write down where we are, okay? Let's write down where we are. We have, according to the formula, ultraviolet, these two multiplied together, right? Ultraviolet. So I'm going to put the x in front of the e to the root x. Minus a little bit of space in front. Okay, these two multiplied together. Are there any constants I can pull out? Yeah, that 2 that's on the bottom, right? So I need to pull it out as a 1/2. That takes care of this. And then you have to multiply those together, right? I'm going to do that on the side. Let me do some scratch work over here just to make sure we're clear on how we multiply those. I'm doing e to the root x. I already pulled the 2 out, so I have a 1 over root x times dx, and then I'm multiplying that times x, right? That's voodoo. That's this times this. And I can slide the x on top there, e to the root x times x over root x dx. And then this I can use, what, college algebra? That's x to the 1 over x to the half, which is x to the half, which is the square root of x. Okay, so all of that just becomes square root of x e to the root x dx. And what do you think about that new integral? You're okay with that? You like it?
You have a square root in both the exponent and in front of the e, so
Okay.
you found, I guess, part of you found part of its derivative, I guess, at least the root x part.
Okay, so, oh yeah, so you're saying if, like a basic u sub, you're thinking more of a basic u sub now or no, Mom? If we did like a basic u sub and let that be u, then this is kind of its derivative? Well, isn't the root supposed to be on the bottom? You know what I'm saying? Like 1 over 2 root x? Kind of. So, I mean, you look at this for long enough, I think, and you start to realize, you know what? This is actually a little bit worse than what we started with, right? I mean, that is a little worse because we've now introduced a root x. I agree with you. If that root x was on the bottom, right? If this root x was downstairs, then you could let u be root x, and then the derivative is there, you're off by a constant. But it's up. That's an issue. Do y'all see that? So what the hell do we do, right? We start over. I'm going to start the whole problem over. Okay? Just because I'm unsure. I'm not crumbling up this paper and not throwing it away. I'm saying maybe I come back and revisit this. I don't know. But right now I'm going to try something different. All right? All right. We already said there wasn't much more we could do, right? Like we tried, we said, let me revisit this. If we just do a basic u sub, why did we not do that originally? Why did we not do that originally? Because the derivative of that's not there, is it? Because if I take the derivative of that, I get 1 over 2 root x dx, right? That's what I get. And I don't see that anywhere here, right? But, watch. Look at this equation right here. What is the root of x for us in this problem? What is the root of x? It's u, isn't it? It's u. See, look, right now, this right here is going to be my u. Do you all agree? I have e to the u right now. The only issue I have is, what the hell is this? What's dx, right? What is dx for us? Well, dx is this right here. I'm going to try and get dx by itself right now by multiplying both sides by 2 root x. That's du equals dx. So I can replace dx, right, with this. The problem with replacing with this is it has u's and x's. And remember, anytime we switch an integral from one variable to another, every variable has to get switched. But, like I just said, what is the root of x? It's u. So I can rewrite this as 2u du equals dx. Do y'all agree with that? And so this basic u sub might actually work for us. It might. We're going to have to write it down and see what happens. But do y'all understand what I'm doing here? Everyone's okay or no? I mean, this is your chance to ask questions. Tried integration by parts. It gave me something uglier. I said, you know what? I thought u sub wouldn't work, but I'm going to go ahead and try it anyway. And I have this like moment where I realize, holy shit, this 2 root x, if I bring it over, I can replace the root x with u, and now I've got dx in terms of u completely, and I can replace that dx with this. And I'm going to replace that root x with u. So what does this new integral become? E to the u, and then what's dx? 2u du. 2u du. That integral is all in terms of u, isn't it? I'm going to continue that over here. So I'm going to write that integral right here. I'm going to write this down. I'm going to go ahead and pull the 2 out of the integral. I'm also going to put the u in front of the e to the u du. That's my new integral. Doesn't that look a lot like, kind of like that integral we had a second ago that was root x, e to the root x, kind of, like a little bit? It looks a little like that, except I don't have the issue of, the complication of the root x and its derivative. Like, the derivative of the square root of x is something complicated. Here, the derivative of u is just 1. So maybe this is going to work for us. Any ideas on how to attack this now?
Wait, so why this time did you pull it out as a 2 out of 1 half?
I didn't. You mean like when we did this problem earlier and we quit?
No. When you just pulled out that 2.
Yes.
Why is that not a 1 half since we're doing u sub?
Well, because I didn't have a 2 over here that I had to divide both sides by 2. It was already on the bottom, so I multiplied by 2. Yes? Yeah, how do you find the antiderivative of that, though? Now integration by parts. Now think about why. Integration by parts says that we're going to choose one of these 2 functions, right? And in the new integral, it'll be the derivative of that one. And then the other function we choose in the new integral, it'll be the antiderivative, right? So what would be a natural choice for the u? U, right? Because what's the derivative of that in the new integral? 1. And what would be the choice for the dv? E to the u du, because in the new integral it'll be e to the u, right? And so that new integral is going to be doable. See, do you see how many steps I'm having to see ahead of things to help myself know where to go? Right? That's why knowing the formula, knowing what you're trying to achieve is important. It's not just like,